अनुकुल सर।
यस सर, गुड आफ्टरनून।
गुड आफ्टरनून, गुड आफ्टरनून। अच्छा, मैं ये बोल रहा था, मेरे को भी है ना को होस्ट बना दो। तो इन केस अगर कोई, अगर मैं अवेलेबल रहा तो मैं उसको एंट्री दे दूंगा, जैसे पार्टिसिपेंट ज्वाइन करता है ना।
ठीक है सर,
ठीक है।
बन गया
ये
आपका
और
होस्ट।
ठीक है, ठीक है सर, ठीक है सर। Good afternoon, George sir.
Hi Sachin, how are you?
Fine, sir. Fine, fine.
Yeah, yeah. I will also join from another device. Okay, two devices I will
Sorry,
have.
sir.
Okay, I will also join from one more device. Okay,
Yes,
just 1 second.
yes, sir. Yes.
Fine.
And sir, participants are still joining, so
Uh-huh.
we will start in 5 to 10 minutes.
Yeah, yeah, no problem.
Okay, sir. Once again, very good afternoon to all of you. And this is the ninth session of this FDP. And the expert for this session, Dr. Nithin V. George from the IIT Gandhinagar. Sir, I welcome to you.
Yeah, thank you, thank you.
Yes, sir. And Dr. Nithin V. George received the Bachelor of Technology degree in Electronics and Communication Engineering from the University of Kerala in 2007, and the Master degree of Technology in Telematics and Signal Processing from the National Institute of Technology, Rourkela in 2009, and the PhD degree in Electrical Sciences from the Indian Institute of Technology, Bhubaneswar in 2012. Currently, he is working as a TECO Chair, Associate Professor in the discipline of Electrical Engineering at the Indian Institute of Technology, Gandhinagar. He had received the Department of Foreign Affairs and International Trade, Government of Canada, and GSEP Fellowship in 2008. Besides, he was granted the Inspire Faculty Award in 2013 and the Indo-Australia Early and Mid-Career Researchers Fellowship in 2017. He was an associate editor for the Journal of Swarm and Evolutionary Computation from 2016 to 2020. His research interests include audio signal processing, microphone arrays, and psychoacoustic. Sir, I welcome to you for this FDP, and really thanks for finding us time from your busy schedule.
Thank you,
Sir,
thank you,
over
thank
to
you.
you.
Yeah, sure. Yeah, it's visible now.
Yes, sir, it is busy.
Okay. Yes. So we want to, uh, yeah, what we want to discuss today is machine learning for audio signal processing. So what I will try to do is I will try to give you some context about maybe some applications of audio signal processing in real life, and how signal processing and machine learning could come as a help in those areas. Okay, so that is the overall objective of this current session. Okay, that's the way it has been designed. So to have an understanding about the problem which we are looking at, what we are looking at is a hearing device. Okay, this is the first example which I am trying to take, which we call a hearable. Okay, what is the hearable? uh, Hearable, he, it's a wearable hearing device is called a hearable. Okay, so our objective is to develop a signal processing solution for people who are suffering from hearing loss. So that is our objective. So first we have to understand what is the hearing loss. What is the hearing loss means? If you There is something called a hearing profile. Hearing profile means there is some frequency versus amplitude curve for your ear. Okay, for your ear, the meaning of this curve. The meaning of this curve is, if I am having a signal amplitude which is reaching my ear, which is above this line. Okay, above this line means if it is above, if it is like this. Okay, so this red line is what I need, and if I am having signal amplitude for whatever I am speaking across the spectral range in the blue zone, in above the red zone, I can say I am able to hear. Okay, fine. But now if the red line shifts up, red line shifts up in the sense, if the red line is suppose this dot due to some changes, instead of the solid red line, I have a dotted red line as my hearing profile. what is going to happen is, what is the amplitude of the signal which is reaching my ear, which is still the blue line. Okay, so in this region of the spectrum, what is going to happen? I will not be able to hear because the signal amplitude is less than my hearing threshold. Okay, under this condition we say that this person is having a hearing loss. So the problem is, even though there are only maybe a range of frequencies for which this person is unable to hear, what will happen to speech? What will happen to speech? Speech is having a large spectral range. Okay, so many of the frequencies you will not hear, some of the frequencies you may hear, and you will lose intelligibility of the speech. So if somebody is trying to talk to this person who is having a hearing loss, that person will not be able to clearly understand the speech or whatever we are trying to communicate to that person. Okay, so this is the problem of hearing loss. Okay, this is traditionally there in old age, but now what WHO is saying is that there is going to be significant young population who are going to have hearing loss because of unsafe listening practices. Okay, unsafe listening practices, and they term, WHO is terming this, that the hearing loss is the new diabetes. This is going to be a very significant problem across a significant spectrum of our population. Significant spectrum of our population is going to have a hearing problem. All of us may have a hearing problem. Only thing is that we don't know that we have a hearing problem. Okay, that's why we are feeling that we don't have a hearing problem. Now, what is the solution to the problem, or what is the technological solution to this problem? See, in the crudest form, what I could think of just amplify this blue line so that it is above the red dotted line, and my problem is supposedly solved. Okay, why this is going to be not that easy? First, because this hearing profile is not the same for every person, and there is going to be spectral what dependence on how much you have to amplify or how much you have to modify my input signal before it is given or played back to my ear. Okay, so in the very crude form, a hearable or an assistive listening device, we call it an assistive listening device. Okay, what is an assistive listening device? It will take some signal, so it will have some microphone, some processing capability, and then you play it back through a loudspeaker. This is the most crudest definition of an assistive listening device. What it should do, it should pick up some sound, it should do some amplification. Ideally it should be a spectrally dependent amplification, and then it should play it back, and it should be played it through the loudspeaker, and the loudspeaker is putting the sound into the ear. Okay, this is the simplest solution to the problem. Now, where is signal processing going to come over here, and what are the type of challenges which we are going to place, and how we could use signal processing or machine learning solutions to this problem is what we are looking at. Okay, this is our problem. Okay, now if you see this ear diagram, what is happening over here? You have some mics M1 and M2. There I have put a DSP unit. Why we need a DSP unit, we will see in the later slide. And then you have a loudspeaker. Loudspeaker is playing the amplified sound, and it is reaching the eardrum. Okay, now let's look at why we need a DSP unit and what are the type of problems which are there in such a device. Okay, so the problem is, this is how a normal hearing aid can look like. This is called a behind the ear hearing aid. There are other types of hearing aids also, and uh, recently all our devices are becoming what, wireless earphones. No, so all the signal processing over here will be applicable to which we commonly call as hearables. Okay. First problem. First problem is, What did I say? I said you have speech. The speech is picked up by the microphone. It is essentially amplified and it is played back. But when my speech is getting amplified, there is a noise which is associated in the background. Okay. Currently, what is happening? I have put fan in my room. So the fan noise is there. That noise is also picked up by the microphone. Earlier it was okay because I'm able to already hear properly. I am saying hello. You heard it. There was little bit of what you can say, the background noise which was there. Now what is going to happen? I have told the algorithm, I have told the device that you amplify that spectral region. But can I say that the noise, the speech and the noise are spectrally separated? You cannot say, because speech has a large spectral range. Noise also has a large spectral range. So there is going to be significant spectral overlap between the speech and the noise. Okay, so it is not a trivial filtering problem. Okay, so I need some solution by which I should be able to amplify, still amplify the signal, but amplify only the speech. Okay, the speech should get amplified, but if I don't do that, what is going to happen? This person already has a hearing problem. I am unable to understand, and then you have put a device in my ear. That device is amplifying my speech hello, but along with that hello, this device is also amplifying the background noise to a very high level. Okay, so this device is of no use to me, correct? Because the noise level also has significantly increased compared to my earlier situation. So I need to develop some mechanism for noise reduction. So this is some algorithmic approach we will have to use. I can use a machine learning solution to the problem, or I can try for a signal processing solution to the problem. But this is not a normal DSP solution, because the speech and the noise which we are discussing, they are not spectrally separated. If they were spectrally separated, what I would have done, I would have put a filter, some low pass high pass filter, and I would have solved the problem. But that is not that trivial in our problem statement. Okay, so this is one area of a digital hearing device where we will need an algorithmic solution to the problem. Okay, so the second problem which we are going to look at is something called an acoustic feedback. Okay, this one, acoustic feedback. Okay, so what happens is, you have this microphone, you have this that processor, then you play it through a loudspeaker. What you can do is that like a you can have an earplug and close your ear. Okay, close your ear, and the amplified sound, this is this red, the red line in this diagram, the amplified sound is reaching the eardrum. But unlike a headphone which we are using now, or in a normal situation, this device is designed to be used 24/7. This is not to be removed, because even when a hearing aid user is sleeping, you need to wear this hearing device, because if some emergency is there, you may not be able to understand that there is a fire. Okay, so you normally they will wear this throughout. So if that is the situation, what we normally do is that we don't close the ear canal path fully by using an earplug. So if I close it, what is going to happen is, I will have something called an occlusion effect. Occlusion effect is, if you are trying to speak and you try to close your ear and then try to speak, what is going to happen? Your own sound will be picked up by the, means you will be hearing your own sound which is amplified. From where it is coming? This is through a bone conduction which is happening in my ear. Correct? So you can try and see. You can just close your ear with your thumb, both the ears, and then try to speak. Your own sound will be looking very different compared to what you are normally hearing through an air path. Air path is when your ear is open. Okay. So that is why traditionally what happens is we try to keep the vent open. Okay. So what we try to do, we try to keep this, we don't try to jam the ear. We will try to keep the vent open. Okay. Why? Because we want to avoid or we want to reduce the occlusion effect. Okay. But now this will give rise to a different problem. What is the different problem? What is the need of a hearing device? You have a sound, the sound is getting amplified and it is now played back through the loudspeaker. But where are the microphone and the loudspeaker? They are very close to each other. So if you look at the hearing aid diagram, what you will see is that this is the position of the microphone and the speaker is also very near to that. Okay. So what is going to happen when you have a microphone and you have an amplifier and then you have a loudspeaker and the amplified sound is fed back to the microphone. Okay. So you have some signal which is coming from outside, which is the speech, and you have an amplified speech which is listening, which is reaching the eardrum, but you have this amplified sound which is again picked up by the microphone. So what will the amplifier do? The amplifier will further amplify it, correct? So this is as if you are in a classroom with a speaker system and you go with the microphone near the loudspeaker. Okay. If you go with the microphone near the loudspeaker, what is going to happen? You are going to have this whistling sound which is going to be there. Why? Because you have a signal is amplified first, the amplified signal is again amplified, further amplified, and then you saturate. Okay. So this will a very uncomfortable situation, and this is the problem of acoustic feedback. Okay. Why this problem is there? Because we have kept an open vent, so the sound is going to be amplified sound, because this is not a normal sound, because you have already amplified, and the amplified sound is going to leak and it is going to be picked up by the microphone, and the microphone, this device, our hearing device, is going to further amplify it, and then this feedback loop is going to be created and you are going to have the problem of acoustic feedback. So I need some solution to this problem. What can be the solution to the problem? Anyone? What should I do to solve this problem? Hmm? Somebody want to say? Can I put a filter somewhere and solve this problem? Can I put a filter over here, this blue color filter, and say that you pass only the speech and don't pass the signal from the feedback path? Can I say, can I design a filter like this? Is it possible? Yes. It is not very trivial. Why it is not very trivial? Because what is the signal which is being supplied? Don't speak. Yes. So my question is, I have the speech. My speech is amplified by an amplifier played through a loudspeaker. Okay. Now what is going to happen is that this microphone, because this is mic will pick sound. Okay. Mic will not care whether it came from me or from somebody else. It is going to pick if you are speaking together. So the speech is picked by the microphone. The amplified signal which is coming from the feedback loop from this direction is also picked up by the mic. Both of them together are again going to be amplified, and you reach the whistling sound situation which we see in a normal setup, classroom type of setup. Now my question is, can I put a blue filter over here which will pass the speech, this speech which is coming from the user, and will not pass the signal which is coming from the feedback path. Feedback path means this path. This path signal is not passed and this speech is passed. Can I have a filter? If I have the filter, this will become again a simple DSP problem which can be solved without much difficulty. Is the question clear now? Abhiranjan, is it clear now? Yes, feedback will include speech also, because what is the loudspeaker producing? The loudspeaker is producing my own, whatever speech was coming from outside only before n number of 200 nanoseconds earlier. Whatever I spoke or whatever somebody else spoke, that only came. No, the problem is it is not good because I want my speech to be amplified. But now, okay, you are saying that you amplify the signal by 3 times. Okay, suppose we are saying. So my input signal is amplified by 3 times. I am happy. But now what is going to happen? Input signal is amplified by 3 times. The feedback signal, which was already amplified by 3 times, will become 9 times. Understood? Correct? So this is a closed loop which has been, a positive feedback has been created over here, and you will not be able to hear whatever input speech is going to come from here, because the significant component is going to be the feedback. This is the problem. Is the question now clear? Abhiranjan, is it clear? Abhiranjan, can you ask from mic?
Abhiranjan, it will be better if you directly ask through the mic. Because in this typing there may be some delay. Abhiranjan, can you hear me? Okay, there is some issue.
No
Yes,
problem.
Okay. Fine.
Feedback. So okay, so the main thing is I don't want feedback to happen. Okay, I want only my speech to be amplified. This is my problem, and it is not very easy to design a filter because both are again okay. Feedback. Okay, feedback means okay, let me, I think all the colors I have used in the diagram itself. Let me take another color. Okay, fine. Feedback means I have a speaker over here. This speaker, the speaker is speaking. This sound is picked up by the microphone. This microphone, what will the device do? It will amplify it. The amplified sound will be played through the loudspeaker. Now, this is what I want the device to do. Now, what is going to happen? That the output of the loudspeaker, which is the amplified sound, can also be picked up by the microphone. Okay, when that is picked up by the microphone speaker, or whether the signal came through the leakage which is over there. Okay, that mic will not understand. Mic is not an intelligent device. In this case, mic is just a mic. Okay, if you have a mic and you speak, and you switch on the what I can say, washing machine on the side, what will happen? Whatever you do in that, if it is a normal microphone, your speech and the washing machine sound both will be picked up by the microphone. That is our situation. Okay. Now our microphone has picked up whatever the speaker is speaking and the feedback. This is the meaning of feedback. Feedback means the in my output is connected to my input with the gain. Okay, my output is connected to my input with the gain. This is the meaning of feedback. Okay, so when you have positive feedback, what will happen? You will have unstable systems. See, if you want to again understand, you can take an simple filter like this. What is this? This is like, this is an IAR filter where I have taken a feedback from where to where. I have taken a feedback from output to this. I have taken a feedback. So now what can happen is this filter can become unstable very easily. How will I check whether this filter can become unstable very easily? I can apply an impulse and see whether this filter is an unstable filter or a stable filter. What is impulse? Impulse is set of zeros followed by a 1 followed by a set of zeros. Okay. So what will happen? I am going to have a 1 over here and I have a previous value of 0. The output of the filter is equal to 1. Now my next input is 0. Why? Because this is an impulse. So my previous input was 1. So this forward path will be output equal to 2 and the feedback path will be 1 into 3. So my total output is equal to 5. Now I have next input 0, previous input also 0. My output will become 5 into 3, 15, 15 into 3, 45, etc. And it will go up to infinity. So now what I can say? I can say that this filter is an unstable filter. So my situation is similar to this. Okay. Why my situation is similar to this? Because I have amplified signal which is fed back as input, which is again further getting amplified without any stop. Okay. So this is the problem of acoustic feedback. Okay. And I don't have a trivial solution to the problem because they are in the same spectral region. Fine. So I will need a solution, a signal processing solution, which is called a feedback canceller. Okay. So till now what we have understood? We have understood that even though this solution looks very simple, what is the solution? A mic, a processing unit, and a loudspeaker. That's all. And then within that processing unit, we have to bring in lot of signal processing because the simplicity will make it very complicated. Okay, understood? Yeah, Abhiranjan, is it clear? Feedback is clear now?
Yes, sir. Yes, sir. Yes,
Okay.
sir.
Uh-huh. Okay. The filter problem is also clear now, that why your filter will not work.
Why, sir? I did not, sir, get this, sir.
So why I am saying is this filter will not work because uh, the noise here is the feedback signal and the speech is what I want to amplify.
Oh,
So
different spectrum, different
no, they are in
frequency
the same
components.
spectral region. Why?
They are the same
Because
spectrum region. That's why we could not filter.
that is the same spectral region. So you cannot use a normal filter over here. Okay.
Yes, sir. Yes, sir. Thank you.
Yeah. Fine. These are two simple problems in the in such an assistive listening device. The third situation is that we have a physical device which is taking signals from the physical world. The sound is in the physical world, in the acoustic world. Do lots of processing in the electronic domain. So this entire gray area is in the electronic domain. And then finally, you will give back the signal again to the physical world. Okay. So you have some signals which are actually in the physical world. Then it gets processed in the electronic domain, and then it gets played back, or it will be fed back again into the physical world. So there is going to be interaction between the physical world and the electronic world. Okay. So when we design algorithms, we will have to take care of such situations where you have an interaction with the physical world, a physical uh, area. So how that will come into my algorithm development is what we are going to see next. Okay, fine. So to understand that, let me give you a problem. My problem is I have somebody at A location who is singing a song. Okay, and there is somebody at B location who is listening to that song. Okay, so A is singing a song, B is listening to that song. Now the same A is also there in my auditorium picture. Okay, and the same B is sitting somewhere within the auditorium. Now A is singing the same song. A is the same person. B is the same person. Both are singing the same song only, like I said. But what will happen? Both of them will experience a different type of a song, correct? So whatever the song I am going to listen to, or whatever experience which I am going to get in my open air theater, is not same as that in an auditorium, correct? So you have A is like a loudspeaker, correct? Because for us, A is something which is producing a sound. A is the loudspeaker over here. B is listener. Listener means B is like a microphone. Okay, B is like a microphone. Okay, so A is the signal producing unit over here. B is acquiring that signal. Okay, and I have a signal X which is getting played through the loudspeaker. Okay, and you have a signal Y which is being received at the output of the microphone. Okay, so X is same in both the cases because I am singing the same song. A is same in both the cases. B is same in both the cases. But Y is not the same in both the cases. Even though all my input signal is the same. That means there is something which the physical world did on the signal which is produced by the loudspeaker. What is the physical world? This region. Okay. Abhiranjan, can you mute?
Yes, sir. Yes, sir.
Okay. So what has happened? The signal X, which is played by A, which is reaching B, there is some physical path in between, which is going to have an impact on what is Y. Okay. In this particular example, I called that entire physical region. What is the physical region? So if you see, at this blue point, the signal is electronic. At this blue point 2, this is blue point 1 and this is blue point 2. The signal is again electronic. But at a point 3 over here, the third blue point, the signal is not electronic. Why? Because the physical output. Okay, so if I want to develop algorithms which are going to be handling signals in the physical world, I need to think of this when I design my algorithm. Okay, I need to think about this. Okay, why? Because I am not processing my signals which are going to be always in the electronic domain. This is what we normally study in a simple DSP course. In a simple DSP course, what we will say? I have x of n is added with alpha of n, which is noise, and you will be told that you design a filter which is going to give reduce alpha and give an approximation. Okay, give an approximation of x at the output. That is a simple problem. Why? Because I am not having any interaction with the physical world. All my signals, x, alpha, all are in electronic domain. My filter is in electronic domain. My output is in electronic domain. I am not interacting with the physical world. But here in our problem, what we have seen is that we are going to interact with the physical world because we are going to develop signal processing solution for the real world. Okay, where there is interaction among two worlds altogether. Okay, so what we normally do is that wherever there are physical systems in my algorithm development situation, I convert that entire physical world into an electronic equivalent. Okay, so in this oval region, everything is non-electronic. This entire thing I can replace by an impulse response. Okay, so now what I can do, see HFN is now in electronic domain. So instead of designing an algorithm for the red diagram, I can now design an algorithm for this. Here I am more comfortable, correct? Because I can understand electronic systems, electronic signals, and my design will be more easy if I think of and design in the blue domain. Okay, so this is what I call the room impulse response. Okay, what is my room impulse response? Room impulse response is the electronic equivalent or the impulse response representing this particular room. Okay, so what is the physical meaning of it? If you sing a song, if you sing in the open air theater, you have some particular HFM. If you sing the same song in the auditorium, you have a different HFM. See, when I am saying hello, all of you are listening to hello, but all of you are listening to a different hello. Why? Because even though X and A are same, the device with which you are listening to me, the room in which you are listening to me, the impulse response of the room in which you are listening to me, all of it are going to be different. Understood? So this is one thing which we will have to be careful when we are going to design algorithms for such audio devices. Okay, so the only three things which we have looked at till now is what? Till now is what is a hearing device, what is an assistive listening device, what is the simplest form of an assistive listening device, what are the simple challenges which can come in an assistive listening device, and we need to develop noise reduction, we need to develop feedback cancellation cancellers, and then I only indicated that we will need to also model physical systems. Okay, this process of converting this physical system into this model is called system identification. Okay, what is system identification? Where an equal system and can be an FAR filter. It can be a neural network. Okay, it can be anything like that, depending on whether you are thinking of a linear system or non-linear system. So this is a simple block diagram or a schematic of modeling of an acoustic path. Why we need to model an acoustic path? We will see in little bit later why we need to model an acoustic path. Maybe I will tell right now only. Then it will be, I think, much more clear. So let's take the uh, acoustic feedback problem once, and then we will try to explain. I'll try to explain why we need to model an acoustic path. Okay. So what is our problem statement? You have a mic, then you have some sort of an amplification. It is getting played. So you have some speech. Okay, so this is our situation. Then I said that this is also going to happen. Speech will come, feedback is also going to come. Okay, this is some filter or some transfer function HFZ. What is that HFZ ideally supposed to do? Depending on your hearing loss, it has to compensate for it. Okay. Now, what is our situation? I want to avoid acoustic feedback. Avoid acoustic feedback means that if I look at the signal at this point A, it contains speech and it contains feedback. And the signal is x of n plus f of n. Okay. At the point A, the signal is x of n plus f of n. Now, can I do something so that yes, yeah, that is correct only. That is the correct understanding. Okay. Yeah. So at point A, you have x of n, which is my speech, f of n, which is the feedback. Okay. Now what I have to do? Can I do something so that at point B, before it gets further amplified, I can get, so this is at point A. At point B, what I want, can I have it an approximation of x at point B? This is our problem statement. Okay. At point A, it is x plus f. At point B, I want f to go. Okay, f to go. Now, suppose I take a signal from point C, okay, and pass it through another transfer function f of z c and subtract it from this point minus plus. Okay, what I am doing, I am taking the signal from point C, passing it through some transfer function f of z and subtracting it from the A signal. Okay, and now suppose the output of f of c is approximately equal to f of n. Okay, is approximately equal to f of n. If suppose it is that, my problem is solved. These two things, whatever were the requirements for A and B, will be met if I can achieve this. Okay, if I can achieve this, my problem is completely solved. Now, the design problem here is what is going to be f of c. What is going to be this box? If I can know the box, I have hit jackpot already. Why? Because even though my mic is picking up speech and feedback signal, which is amplified, my user is not listening to the feedback signal because I said that this green box is producing an equivalent of the feedback. Okay, so what should be the characteristic of the green box? Anyone? What should be the characteristics of this green box? Yes. Anybody want to try? You can type in chat also. Okay. Question is clear? Is the question clear? Question is, what can I say about this green box for this feedback cancellation to happen? Yes. So fine. So what F should do? So suppose F behaves similarly to this entire path, this green line path. If the transfer function F has a transfer function similar to the path shown in the green line early upper path, what is going to happen? Whatever signal at C, if it would have created feedback, it would have passed through where? It would have passed through like this. Now I have created a model of that path, model of that acoustic path, and kept it over here. Fine. So what will happen? So when the C signal will reach A, I already know what is the C coming at A because I have created a model inside over here. Understood? Now you should understand why we need as a modeling as a critical aspect in algorithm development when we are dealing with physical world. Okay, that is why we are doing here our modeling of an acoustic path. Okay, why we need model? We are finding an equivalent of electronic equivalent of a physical path, electronic equivalent of a physical path to solve in our first example an acoustic feedback problem. Okay, an acoustic feedback problem. Okay, again this is not implemented like this because this feedback path is not fixed. If you move your head, this path will change. If you keep a mobile phone near your ear, this path is going to change. So this f of z also has to be adaptive. Okay, the filter characteristics also should change. Fine. So if I want to do a modeling, what I should do? I should have an input signal, pass it through the physical world, pass it through the model. This model can be an FIR filter. It can be a neural network. Depending upon when will I take an FIR filter and when will I take a neural network? Yes, anybody? Under what condition will I take a neural network as a model, and under what condition will I take an FIR filter as a model? Hmm? Yes, Aviranjan. Under what condition we will take a neural network, or under what condition we should take an FIR filter? Hmm? So I have to decide on what model to take depending upon, okay, depending upon what I know about the characteristics of the physical path. If my physical path contains non-linearities, if my physical path is non-linear, what is non-linear meaning? What is the meaning of non-linear? Non-linear means what? So, what is the specialty of non-linear system? So, I am saying that I have a box over here. This is non-linear. Is this a good box or bad box as far as signal processing is concerned? Is it good or is it bad? Bad box. Why it is bad box? Okay, why nonlinearity is bad? So if you see your DSP textbook now, everywhere what we will say, when we write the first problem, we will say assuming that the system is LSI or assuming that the system is LTI. This is what we write in our DSP codes, correct? Now I am saying that this box is non-linear. What is the problem with this? So I am going to play a song through a non-linear box and you are going to get some output. And I am going to play the same song through a linear filter and I am going to get an output. What will be the difference in both the cases? Yeah, somebody? Yeah, song is different. Why it is different? Anybody other than Abhiranjan? If somebody wants to try. Okay. Yeah. Yeah. Okay. So what is my problem? My problem is suppose my nonlinearity is a square nonlinearity. And if I apply sine omega n as input to the system, my output will be sine square omega n, which is equal to 2 omega frequency will come, cos 2 omega will come. So if I am applying a 100 hertz input to a nonlinear block, I can get a 200 hertz output when I took a square nonlinearity. Okay. But if I apply a 100 hertz input to a linear shift invariant block, whatever you do, I will not get a 200 hertz output. Either my 100 hertz will be there, 100 hertz will be amplified, 100 hertz will be reduced, but it is not going to generate new frequencies. But the moment you bring in non-linearities, what is going to happen? It can create new frequencies. The moment you create new frequencies, that is not the same song which you wanted to play, correct? Because you created a music which contain 100 hertz only, and now what has happened? Your device has made it appear like 200. So when you have cheap loudspeakers, what cheap loudspeakers will do? Cheap loudspeakers are not linear elements. Okay, they are typically non-linear elements. Square or cube nonlinearities will come in a loudspeaker. Okay, so when I am going to design a device, if I am going to design such a device with all high-end loudspeakers and microphones, because finally when I want to make my hearing device, I need to not only develop signal processing algorithms but also have sensors and actuators. Sensors and actuators means I want loudspeaker and microphone. The moment I have loudspeaker and microphones, or specifically loudspeakers which have non-linearities, modeling should not be done with an FAR filter. I should be thinking of a non-linear modeling, or I will now use a neural network to model this physical path. Why we need modeling? We saw earlier in a simple example of feedback that why it is critical for us to model the path. Model the path. Okay, fine. So now, okay. So if I am going to use a linear model, this is my linear model. I can use an adaptive FIR filter to model it and use a cost function, some error square type of cost function or an MSC cost function, and update the parameters of the model like what we do in a normal neural network. This is what we can do if I am thinking of a linear modeling task. But like I said, this is ADC, okay? Like I said, if my physical devices contains non-linearities, I need to think of a non-linear model. Okay, so I have to decide what should be the non-linear model which I should be using. So the system identification which we were doing earlier, or the modeling which we were doing earlier, is no more a linear system identification. It is a non-linear system identification. So I will have to use an appropriate non-linear model for doing the system identification. So some of the popular non-linear models, one model is called a Wiener model. In Wiener model, what I have is I have a linear block and a nonlinear block in cascade. So I have a linear block and a nonlinear block in cascade, and this entire thing together is called the model. Okay, so the linear I can take an FAR filter, nonlinear I can take an RBF or an MLP or some nonlinear neural network I can take over here. So this is one such model I could take, which is called the Wiener model. I could take something called a Hammerstein model. What is Hammerstein model? It is simply an N and an L in cascade. Earlier, an L and N were in cascade. Now N and L are in cascade. Okay, because these are not linear, you cannot swap it. Okay, swapping is not safe. So this is another decision I can take, whether I want to use a Hammerstein model to do the system identification, or I want to use a Hammerstein-Wiener model to do the system identification, which is called an NLN model. So this can be an MLP, this can be an FAR filter, this can be an NLP. Understood? So these are the type of decisions which I will need to take right now if I want to do a modeling task. Okay, not a simple MLP only. Okay, want to do an acoustic modeling task. Understood? Okay, fine. So this is one simple example. Simple example means if I have a nonlinear system, I can have, like I said, an FAR filter or some neural network, sorry, reverse neural network and some linear network, and together it will act as the model, which is going to be the electronic equivalent of the physical system. Okay, why are we talking about all of those things? Because earlier I said this, that I want to create an electronic equivalent of the physical path, and then later I said the physical path can contain nonlinearities, and when the physical path contains nonlinearities, you don't use a linear model, you will need a nonlinear model. Now you have to decide what type of nonlinear model to use. So the three models which I discussed are standard models which can be used, but I will have to decide what N and what L to be used in my particular application. Okay, in my particular application. Okay, so this is one application where we will need to use a machine learning solution if needed, because if it is linear, I am okay, I am handling linear signal processing. Otherwise I am going to handle non-linear signal processing. So if you see adaptive signal processing books, they will also call this non-linear signal processing instead of calling any machine learning or neural network based approaches. but similar same things you will see. Non-linear signal processing is what we will need to do. Okay. So now if I want to look at simple non-linear models, instead of going deep in the sense I am not looking at multiple layers of neurons, and I want to do some of the tasks, because I am not looking at a, see what is my requirement. My requirement is I have a very low power device. Okay, because these are battery operated devices which are supposed to be used 24 hours, and I cannot create overcomplicated solutions to this problem. I need simpler solutions, but I cannot also say that everything is linear. Why? The moment I say everything is linear, I need to buy the costliest loudspeaker and the costliest microphone to make my device. Correct? So if I can allow for some degradation in my signals by allowing little bit low cost speakers and microphones, now if I can do some nonlinear signal processing, I may be able to get a good solution to the problem. Okay. So one direction in which we could look at is to not go for deeper network. That is one direction. Going for deeper network is another direction which can be thought of. So suppose I am not going for deeper networks, I could think of single layer neural networks. Okay. Single layer neural networks in the sense I don't want to do a backpropagation. Backpropagation is what I want to avoid. Okay. So what I will take help of is I will take help of the Covers theorem. Covers theorem is a 1965 theorem, not a new theorem. Okay, it's a very old theorem. What it is saying, what is Covers theorem saying? Covers theorem is saying that a complex pattern classification problem cast in a high dimensional space non-linearly. Okay, the two things which you have to look at is high dimensional space and non-linearly is more likely to be linearly separable than in a low dimensional space. This is the Covers theorem. Okay, so what is the basic idea of Covers theorem? I am going to design some neural network. Okay, but I don't want to use an MLP, or where I need to use a backpropagation, or where I need to look at multiple layers of neurons. I don't want to do that because I have very limited resources available with me, and I am thinking of single layer neurons where backpropagation is not required, and I want to bring in Covers theorem as a possible direction to look at. So what Covers theorem will do is you have some input which is in some dimension, suppose 2 dimension. I expand the input to a higher dimension, suppose 10 dimension. Okay, using some non-linear function, and after the signal has been expanded, I only need a linear network to find my final solution or the final output. Okay, so instead of the L and N and the Wiener and the Hammerstein, all those things which we discussed earlier, I am now thinking of a simple network where you have an input. The input is expanded to a higher dimensional space, and then after the expansion in the higher dimensional space, you are dealing with an adaptive linear network. So the only adaptation which is going to happen is in a linear network, not in a nonlinear network. Okay, so what is the idea? The idea is you have an input. Input is expanded to a high dimensional space. So what is high dimensional space means? I went from 2 to 10. How I will go from 2 to 10? We will take an example and see. Okay. So we go from a low dimensional space to high dimensional space. And when I go from this 2 to 10, I should use some nonlinear function to do that. What is nonlinear function? I can have a sine, I can have a cosine, I can have a tan h. Okay. So like this, some nonlinear function I should use to do this expansion of dimension from lower dimension to higher dimension. Once I have expanded, I only have a linear adaptive network after the expansion, or in the 10th dimensional space you only have a linear network to be updated. Okay, this is the basic idea of cover theorem which we use in RBF also. Okay, similar ideas we will use in RBF. Or I could think of a class of networks called linear in parameter non-linear network filters. Linear in parameters. Linear in parameters means what are the parameters which are updated? The parameters which are updated are, these are the only parameters which are updated. Okay, so as far as parameters are concerned, this entire thing is linear. This entire thing is linear because parameters update will only see updation in the linear part of it. Okay, these are called linear in parameter non-linear filter. These are usually single layer neural networks like the functional link artificial neural networks. There are other classes of neural networks called the generalized flan, and so many other type of neural networks are there. Okay, so when we are thinking of neural network, we don't have to essentially always think of deeper networks. We could also think in the other direction, because your application may not have the available resources or available data for that particular problem to be solved. So suppose we look at a flan. I am taking a flan over here. What is this flan? Flan is, you have an input signal x. I create a delayed tap delay line from x. So that is x. This is x of n minus 1. This is x of n minus 2, etc. Then I do a non-linear expansion because cover theorem told me that you do non-linear expansion. After expanding, we will see in the next line what is the expansion. Next slide. You multiply the expanded signal with W0, W1, etc., Wm minus 1. Multiply, add them together to get an output. And we update the multiplier values only like we do in any normal neural network. Okay, and depending on what is the nonlinear expansion which we are looking at, you will have different types of neural networks. So if I am using a trigonometric expansion, my expansion can be like this. Okay, expansion can be what? I will put a 1. I have x sine pi x cos pi x, sine 2 pi x cos 2 pi x, sine 3 pi x cos 3 pi x. Then I have x of n minus 1. I do similarly. I will have sine pi x of n minus 1, cos pi x of n minus 1, etc. Understood? So suppose I have input, and this is what I am expanding. Okay, functional expansion. So what is over here? X of n, x of n minus 1. So I call this the x1 vector, which is x of n, x of n minus 1 transpose. Now I am doing functional expansion. Okay, functional expansion I can write x2 vector, which is equal to 1 x1 vector. So ideally it should be bold small, but here I have put capital. Okay, then sine pi x1 cos pi x1. Okay, this all should be transposed ideally. Okay, fine. So now what is happening? So this x1 vector is of what dimension? 2. So this x can be the speed signal which is coming. Okay, so some one dimensional signal. So this is of this is 2, this is 2, this is 2, this is 1. So my x2 dimension is 7. Okay, so from a two-dimensional signal I have now gone to an x2 vector. So this is my x2 vector area. So I will need how many multipliers now? I will have 7 multipliers, and then I add all of them together to get one output. Okay, and I am going to update these parameters. Understood? So this is the basic idea of a trigonometric flag. So here I have used a sine and a cosine functional expansion. Okay, but I can use other type of expansions also. Okay, why I have used a sine and a cosine expansion here? Anybody? So what is my objective? My objective is to do this modeling. Okay, my objective is to do this modeling, and instead of using a linear model, now I am using a trigonometric plan here as a model. Why trigonometric plan? Because I am having a path which contains nonlinearities. Okay, see. Yes, yeah. So this sine and cosine, see, our motivation was what? Our motivation started from Cauchy's theorem, which said I have to go to high dimension. So that's why I went from 2 to 7. And it also said you should have nonlinearity. But here I have used sine and cosine nonlinearity. Okay. But why sine and cosine nonlinearity? What is the speciality of a sine and a cosine nonlinearity? What is the speciality? Why sine and cosines are very simple and very nicely used everywhere? What is the speciality of sine and cosine? Why I have used sine? That is the question. No, yeah. Why sine and cosine? Why sine and cosine? Anybody else? Yeah, I said I am expanding it. I expanded it. I created a vector. Okay, I got an expanded vector. I got an output, and you will get good results. Okay, it's not a bad network. It's a good network. Yes. So the basic idea is from what we study from Fourier series and Fourier transforms. Correct? Okay. So I am trying to, if I have a signal under some certain conditions, what I could do, I could say that this signal is composed of sine waves and cosines of some amplitude, some frequency, some phase mixed together. So what is our objective? Our objective is to create a model of some nonlinear system. Okay. Okay. So let me not. I think it's clear. Eh? So that is the idea of this. Okay. Fine. So why we are doing all of those things? Because we have to do the model. This is another type of neural network. You can have a look. This is called an adaptive exponential plan. So where we use a decaying uh, sinusoids as the basis function to create a neural network. Okay, so I can have a decaying sign, I can have an expanding sign, and the rate of decay can also be adapted. So this is the parameter update over here, where alpha is the parameter which is going to decide how much I should decay the sign or how much I should expand the sign. Okay, so you can just have a look at this network. Okay, this is how the expansion will look like. Okay, so you have an e minus a sine pi. This is going to give you significantly better output or a better modeling performance compared to a trigonometric fly. Okay, so this is how finally a Hammerstein model is going to look like. Okay, so this network is the n, this is the l, and I can decide which n I should be using over here. Okay, so fine. Now let's go back to our previous case of feedback cancellation. So this is my solution finally. What is my solution? This is my direct path. This is my feedback path. This is the cancellation path. Where in the cancellation path, you have an adaptive filter which is going to take the signal which is going to be played through the loudspeaker and modify it and subtract it from the output of the mic. So I have a plus over here and a minus over here, and you have a signal which is going to approximate the desired signal which is going to be played over here. Okay, so this is the basic concept of feedback cancellation and how signal processing is going to come over there. And when nonlinearity is there, we can think of uh, neural network based solutions if needed. Okay, I will come back to this if I get some time, but let me go to the I will just skip these two things. So this is how we finally implement the algorithm. So how will you finally implement an algorithm? So you developed an algorithm. What is the guarantee that your algorithm is going to work? There's no guarantee that your algorithm is going to work, because you may get a graph which says that the algorithm is working. So what we could use is something called a dummy head microphone. This is actually a mic. So you develop your algorithm, you have a device which is kept on the ear of this dummy head. Okay, and the algorithm is going to run in some processor. Okay, and there is outputs from this device which will say what is the. So now if I am playing speech outside and you run my algorithm, I will be able to get clear speech without feedback at the output of this dummy head if my algorithm is good. And what we normally use is we use a speed code. Uh, uh, this is called an audio target machine. Okay, see over here, you have a set of mic inputs and you have a set of loudspeaker outputs, and you have a powerful processor which is going to implement the algorithm which we are actually running. Okay, this is how we finally you will have to test whether your algorithm is going to work in the real world or not. Okay, this is just for your information. Fine. Now let me take you in the other direction. I want to do a noise reduction. Why I need a noise reduction? Why do I need noise reduction? Because I said if I do a symbol amplification, not only the speech signal which is to be amplified will get amplified, the noise also will get amplified. We don't want that to happen. So my device should amplify speech and not amplify noise. So somehow from a signal which is speech plus noise, I have to recover speech. And I could use a data driven approach for that problem. Okay. So our approach is like this. Approach is you have an input speech. So we will need training data for this. So I have a speech database. Speech database contains hundreds of pure speech, okay, without noise. Then I have a noise database, okay. It will contain different type of noises which are available, okay. Now suppose I train a network in such a way that I mix noise and speech, both are available with me, and tell the network that my desired signal is the pure speech, which is also available with me because this is from my own database, correct? Then I should be theoretically able to develop such a model so that after the training is over, if I apply a noisy signal to this box, speech plus noise, this model should ideally create a noiseless or a less noise speech out of it. Okay, this is this possible solution if I want to use a machine learning solution for noise reduction. Okay, so now how to handle it and what type of algorithms can I use, what type of networks can I use, how will I implement that algorithm? So typically what we do is that you have a speech is one dimensional signal, you buffer it means you divide it into smaller groups. So I have got an X vector over here, okay. So you have a speech, you took a segment of a speech, then you took an STFT of that input signal, okay. So you got one segment of the speech, now you are taking an STFT of that signal. What is STFT? Short time Fourier transform. What will short time Fourier transform give me? Short time Fourier transform will give me time versus frequency versus amplitude, some representation I'm going to get like this, okay. Time versus frequency versus amplitude, correct? This is what short STFT is going to give me. So Fourier transform is what? Fourier transform is a complex quantity. It will have a magnitude and a phase. So you take the magnitude of that STFT. So this is the magnitude matrix of that STFT. So you have a speech segment X, you take the STFT of that, you will get a matrix. That matrix is of dimension m cross n. Some matrix is there. This contains complex quantities. I take the magnitude of that, and that magnitude is the X vector. Okay. It will also have phase. That phase I took in this direction. I am not doing anything on the phase. Okay. Because finally I will need magnitude and phase to recover the speech. Okay. Because I don't want to finally, I have no use of STFT. I am only concerned with speech. Correct. So I start with a speech, I buffer it, I create a vector X, then I take an STFT, I got another matrix, capital X. Capital X is a matrix over here, which is a time frequency matrix. Okay. and the magnitude of it. It will be like a colorful STFT plot, time frequency plot. Now what I am going to do is I am going to apply this matrix to a denoising model. This denoising model can be a well-known solution from an image processing or a computer vision task, because significant advancement has happened in that domain, correct? So a lot of work has happened, lot of networks have been created already. Now as far as that network is concerned, we are giving an input image. What is that input image which I am applying? The input image which I am applying is the magnitude of the STFT, which is an m cross n matrix of non-complex values, because this is only the magnitude. Now I tell this denoising model that I want a denoised image which is again m cross n, which is the STFT of the same buffer, the same length x of speech without noise, because speech without noise is already available with me, because I have created the, this is I say I'm saying from the training point of view at the training phase. Okay, so what I am applying, I am applying the matrix m cross n, which is the magnitude of the STFT of the pure speech segment, that is applied given to the denoising model. So what is the denoising model having as input? I have an input which is the magnitude of the STFT of speech plus noise. The model has a desired output which is the magnitude of the STFT of the pure speech segment. Now I can train the network, because this is like an image processing task, image denoising task, but our images are magnitude STFTs. Okay, magnitude STFTs. These are our images. Okay, fine. Now if I train it, this network will be able to give me denoised STFT magnitudes. Now I combine the phase and the magnitude, where the denoised magnitude spectrum is combined with the noisy phase spectrum to get back a complex matrix of M crossing. Okay, because initially I had one-dimensional speech, I buffered, I created vectors, then I applied STFT, I got a complex matrix, I extracted the phase, extracted the magnitude, did some processing on the magnitude of the STFT. Okay, after the processing of the magnitude of the STFT, combine it with the phase of the original noisy signal. Then after combining, you do an ISTFT, inverse short time Fourier transform. Once you have an inverse short time Fourier transform, you will get back again in the time domain. But this is only a small buffer, small segment of the speech. Now you concatenate your outputs and you get a denoised speech. You can have an LSTM as a solution, or here you can have other networks as solution, because we are not putting a lot of concentration on what is the denoising model, because as far as the denoising model is concerned, it is not dealing with speech at all. It is dealing with a time frequency matrix, the magnitude of the time frequency matrix, and the network is also given what should be the magnitude of the time frequency matrix for a pure speech. Once all the training is over, what I can say, once what I will take out, I will take this out and apply another noisy speech. Okay, and ideally the network should give me a denoised speech segment output. Okay, this could be a data driven approach for noise reduction. Okay, If you have not tried, you can have a look at crisp.ai. Okay, so they have a beautiful add-on uh, which can be put on your system right now, which will denoise the background noise. So when you are in a Zoom call or a Google Meet call, it can override the inbuilt noise reduction and take it through crisp.ai's noise reduction algorithm and significantly reduce the background noise in all your calls which are there. Okay, fine, you can have a look crisp.ai. So this is the second another area where significantly machine learning can come and help in signal processing application. Application is signal processing because I want to use this in a hearing device. In the current form, it may not be possible. Why? Because there is significant computation even after the training. Even if it is pre-trained, the computation is on the higher side over here, but it will be possible in the future. Okay, so this is what happens in the noise reduction. Any doubt till now?
Sir, why the means we have to reconstruct that noise means the self interfering speech signal. So why means this is the very obvious that STFT is done, but how the STFT include or inculcate or differentiate between the intended speech and the interfering speech, and how
Yeah.
the denoising has differentiated the both signals. So I want to know how this block diagram accomplish that task.
So this is not the feedback cancellation task. Okay, this is the noise reduction task. So the noise reduction task is where I said you are speaking and in the background you have a washing machine running. Okay, so that is the task which we are looking at. So in when we did experiment, what we did is we did measurements. We wanted to reduce wind noise. Okay, because now if I keep my microphone near the fan, you will have wind noise, correct? So you are not canceling two speeches. That is not the objective. Okay, so if you do a Zoom call and in the Zoom setting you go to the noise reduction algorithm and select high, if two people are speaking from your side, both the signals will go. But if there is a dog barking in the background or some loud other noise which is there, that noise will not go into my Zoom call. Okay, this is not a feedback cancellation problem. This is a noise reduction problem. Okay, so there will be spectral overlap. Okay, there will be spectral overlap, but that is where adaptive signal processing or machine learning is going to give you a solution. Even when you have a spectral overlap, you should be able to what segregate the signal and the noise. See, we can mathematically prove it. How we will be able to separate the signal and the noise, even when the signal and the noise are in the same spectral region. So it has to do with correlation of two signals. Okay, but this problem will be more complicated in the feedback cancellation problem because there is high correlation also between the signal and the noise in this problem. Okay, if you look at acoustic feedback cancellation, the signal and the noise, they are highly correlated because the noise is also another speech. Not only speech, it is my own speech. Okay, so there will be high level of correlation between signal and noise in that problem, but not in this case because this is a noise reduction problem which we are looking at. Practically this can be wind noise. Wind noise is going to be a significant type of noise in all of these devices. Yeah, Abhiranjan, is it clear?
Yes, sir. Clear, sir. Thank you, sir.
Yeah. Any other doubt? Anybody?
So,
Ah,
may I ask, sir?
yeah, yeah.
It will be, sir. But at the end, sir, how the neural network or any non-linear network, the mathematics behind demerging from speech and unwanted
Ah,
image.
is it in this problem? Are you asking?
In this regard, also, it might be more helpful, sir, to understand demerging, sir.
Correct, correct, correct. Yeah. So if you want to see, the problem is we can understand it. I will show you sample on how to understand the behavior of a neural network. Okay, what type of analysis has to be done? See, the problem is we can take two extreme directions. One direction is where we say you have a black box, you apply a signal, you apply a training signal, and you are done. Second direction is to look at why this is working and how this is working, and can I do an analysis mathematically to show whether this is right or this is wrong. I will only show one paper. I will show our own paper only to understand the complexity of the analysis. Okay, just to understand the complexity of the analysis. Then I think you will get some sense of it, because we need to put lot of time and effort to understand that. But if you want a solution to the problem, it is not that difficult, because even if you don't understand it, we will be able to get a solution. So let me show you this. So this is a 2021 paper. Okay, see, it's our own paper only. This is neural network and learning systems paper. The only, we are not developing any new algorithm in this paper. The only thing we are doing is convergence analysis of a particular neural network. This network we developed some 4 5 years ago, but we only did what? We only did convergence analysis. Okay. Let me show you what is the type of analysis we, even I will not be able to explain, because finally when I showed in the slide, I showed only equation number 1, where I said this is the expansion which is going to be there, and I said after that you multiply and add, and you are going to get the output, and you will be happy, you should be fine, and you will be able to apply this in your particular application, whatever is the neural network application you will be able to apply. But the fundamental question is why it is working better. You are getting an output which is good, but how do I know that this is right? And so that is where we will have to do convergence analysis to see. This is the type of analysis I will not be able to understand, and I will not be able to explain also what is written over here. Okay, so some math has to be done properly. Okay, so from that one equation only these 65 70 equations are written, and finally what are we trying to prove? What we are trying to prove is, can I get a simulation result which is matching the math which we wrote? So we wrote some math and we got some random equations. Okay, can I prove that my simulation and theory are matching? That is where my analysis will become complete. See, when I take up a problem, suppose noise reduction or feedback cancellation, I applied a network, I got a result. My solution is there, my output is there. That is not good enough. Why that is not good enough? That is good enough as far as application is concerned. That is good enough. But if I want to develop a new neural network, or if I want to understand much more into a neural network, then I will have to understand the, go a little bit deeper into it and do the analysis and then prove and how it is going to converge. Okay, so those type of analysis we will have to do and show that this is how your theory and simulation are going to be matching. Okay, so that will be, I think, out of scope. It will be very difficult to explain these things. Uh, only once a full PhD can be done on only analyzing uh, a simple network. If we do more deep into it, okay. Yeah, yeah. Anything? Any other doubt? Anybody else?
Yes, sir. There is no doubt anymore. You have presented this topic very nicely. It's very thank you very much, sir.
Thank you. I have 2 3 slides. Okay, let me just finish that also. Okay.
Yes.
Yeah. So this is the so this next application which you can have a look is active noise control. So active noise control means which this is what you will see in ANC headphones. It's the Bose or Sony ANC headphones, which very popular now. The basic idea is what? The basic idea is you have a sound, you produce another sound, and cancel the sound. Okay, this is the basic idea of active noise control. If you get some time, just Google for G impossible unimpossible. You can't unring the bell. There is a nice video which will explain very beautifully what is active noise control and how it is applied in a practical scenario. So these are applications. So you will see in Bose headphones, Apple AirPods, even in Ford Endeavor 2020, you will have active noise. The idea is what you want to reduce engine noise within the cabin. Okay, so you use some signal processing solution to reduce the engine noise within the cabin of the car. This is the basic idea. The basic idea is you have a noise source. This is the engine which I said. So some sound is there which is reaching the people over here. Now what I am going to do is I am going to generate another sound. Okay, sound is not like the sound is longitudinal, but I'm just drawing it like this. Okay. So generate another sound. Generate another sound means I will have to add an additional loudspeaker. That sound which I am going to produce should have characteristics of the sound at this point A. So I put a microphone over here, which I call the reference microphone. Then I should also know how much noise has been cancelled finally. So I put a second microphone called the error microphone. Okay, so typically, if I want to implement an ANC in a particular system, I will have to now insert additional loudspeakers and microphones. Then do some sort of a signal processing. This signal processing, as I said, can be linear signal processing or it can be nonlinear signal processing. If it is linear signal processing, what I will do? I will use an FAR filter, something like that, to do the signal processing. If I want to have a nonlinear, why nonlinear signal processing? Because again, I have got loudspeakers, I have got nonlinear elements. So the signal processing can be nonlinear signal processing. Then I will use neural network or FLAN or any of those things to do the process. Let me see, that is the basic idea. Okay, because I think I will not be able to explain the algorithm, but let me explain a little bit about the headphone. So what is our idea? Our idea is I want to listen to music. So that music has to come from here. music is getting played. So some loudspeaker is there, music is getting played. But I have background noise. Okay, so if I am playing this music in a railway station, what will I normally do in a normal headphone setup? I will increase the volume and try to listen to the music because I have significant background noise. So I will finally end up with significant hearing loss because I am exposed to loud noise which I have generated. But suppose I have a mechanism by which I could reduce the background noise which is reaching my ear. I will now be able to play my music at a lower amplitude, lower sound level compared to what I was doing earlier. This is the idea and application. Because if I am doing active noise cancellation, what I can, in the crudest form, what I could do is I could put a microphone outside the headphone. You have some sort of a processor, then you have some sort of additional loudspeaker. You can have some mic inside the headphone also, and then run the algorithm. Tell the algorithm to reduce the noise at this point. So what the algorithm will do? Algorithm will try to generate new sounds through the new speakers, but it should not cancel the music also. Okay, music I want to listen without any distortion, but I want the noise which is there in the background to be cancelled, and my noise level will reduce. So this is the basic idea of active noise cancellation or ANC headphones. Okay, but they may not be doing exactly like this because different devices will be doing differently. Sony XM4, XM3, these are very good uh, ANC headphones which you can have a look. But the moment we put all of these things, you need a processor inside a headphone, you need a power supply inside a headphone, you need additional microphones inside a headphone. So that's why you will not get it cheap because there is technology and processing happening. This is an active device which is doing a lot of signal processing in real time to make this happen. Okay, so the type of algorithms which we discussed earlier can come over here also. So this is another application to look at where uh, these type of adaptive signal processing or machine learning can come. Okay, so these are some of the references. You can have a look if you want to understand digital hearing aids. James Gates, there is a hearing aid book that is very good. If you want to understand adaptive filtering, Dennis 2020 book is there. This is again very good. If you want to look at simple neural network without any hi-fi things, you can look at Hagen's neural network design book, which is available for free on this website. In the others, very simple. If you don't want to, you want to understand and do things fast, this is a very good book. Hagen neural network design. Yeah. Anything else? Any doubt?
Any question from the side of participants? You can write in chat box also.
Yeah. Yeah, I will send the slide to Sachin. I will send the slide to you. Okay.
Yes, sir. Yes, sir. Thank you, sir. And if there is no question, then we are going to end this session. And thank you, sir, explaining in a very with basic to advanced about the. Okay, sir. One question is there.
Yeah, yeah.
Denoising is done in short and then based Abhiranjan Singh.
Okay. No, this is old one.
Okay, old one. Okay, old
No,
one.
no. I think this is new only 354. I think Abhiranjan got enough answers. I think that's why.
Yes, sir.
Abhiranjan, thank you so much. I think normally it's very difficult to get questions in online FDPs. Okay. good that you asked. Okay, very good.
Yes. But sir, you have explained all things and clear most of the doubts, or not most of the doubt, all the doubts of Aviranjan regarding this presentation. And I can say this is the one of the best session of this FDP. And those who are working in the field, they will get the more ideas in this field, audio serial processing. And those who are planning, they will get the fundamental from your lecture. So really, thank you, sir, finding us time from your busy schedule. And thank you so much, sir.
Thank you so much. Okay, bye.
Thank you, sir. So thank you, all of you. This is the end of this session, and we will share the feedback form on WhatsApp group for this session. Thank you, all of you.